Hey everybody, welcome to New York State Manufacturing Now, the podcast that's powered by FuseHub. I'm your host, Steve Melito. Today, we're talking to Dr. Michelle Crimi, co-founder of Remwell in Potsdam, New York. Remwell is the only company that offers fully on-site, in-place, permanent treatment of PFAS, contaminated groundwater, and at a competitive cost. Dr. Crimi is also a professor of environmental engineering at Clarkson University and is the dean of the graduate school there. Michelle Crimi, welcome to New York State Manufacturing Now.
Thanks so much, Steve. It's a real pleasure to be here. Thanks.
Wonderful. So, Michelle, what are PFAS, and why are they important enough to worry about when there are so many environmental challenges?
Yeah, that's a great question, Steve. So PFAS are thousands of man-made fluorinated compounds that have been used in a really wide variety of industrial and commercial products. And through their manufacture and through their use, we've been subject to widespread environmental contamination, including our water and our groundwater. We're focused on the groundwater. Now, at very, very, very low concentrations, like parts per trillion, a drop in an Olympic-sized swimming pool, these compounds are toxic. So they're widespread and they're highly toxic. So they really present quite an environmental threat.
Wow, and I think I remember reading something about a significant amount of groundwater or maybe drinking water in the U.S. being contaminated with PFAS chemicals. Is that accurate?
That is accurate. While the full scope of the problem is not yet well understood because there's still a lot of sampling going on, we do know that PFAS can be found in 96 to 98% of the blood of all Americans. And it is an international problem as well. It's not just a problem in the U.S.
Wow. So how did your work at Clarkson shape the creation of Remwell? In other words, was there something you learned or discovered that was too important not to pursue?
Yes, and I love that question because there was a few aha moments. So yeah, I have over 20 years of experience developing and testing environmental technologies for treating contaminated groundwater. My expertise in the past has been using chemicals that are innocuous to destroy, the chemicals that we don't want as contaminants in our water. And we started to hear about these PFAS compounds and forever chemicals, and they're, extremely difficult to break down. And the technologies that we've been using for years, that we've been developing for other contaminants, simply aren't going to work for PFAS. And so we started out doing some testing. And yeah, that proved to be true with our technologies as well initially. So we started to dive into the literature and what's out there that can break down these compounds that we're not using on an everyday basis in the world of treating contaminated groundwater. And we started to come across destructive technologies like the use of ultrasound. And I'm sure we'll come back to that in a little bit. But while we were working on that, we were also part of a project team that was exploring the use of horizontal wells to hold reactive media that can actually break down contaminants. And so when we think about drinking water wells, we always think about something that you poke down straight into the groundwater. But here we're talking about horizontal wells. So they run underneath the groundwater in the direction of groundwater flow. So we can take those bigger wells, we can put reactive carbon or reactive iron in there, and they can either absorb or break down contaminants. Well, there's no media out there that would break down PFAS. We like the use of the horizontal well because it captures water without having to do a lot of pumping. So pumping water is really energy intensive, it's expensive. So if we could get those wells to focus flow and funnel water and put something in there that would treat PFAS, then we have a really efficient and effective system that would destroy PFAS. So that was our thinking when we started to try to figure out, well, what can we put down there? Well, there's not a media available that will break down PFAS. What will break down PFAS? And that's where we started to look into the use of sound waves and the idea that that's something that we could actually design to put down inside of a horizontal well.
Got it. So I think you've answered part of my next question in part, and we're going to talk about your technology in more detail, but what are some other existing ways to treat contaminated groundwater, maybe with PFAS, maybe without? But I guess what I'm really getting at is, why do you need a new technology to do this? Isn't there something that already existed that we could have just used instead?
Yeah, that's sure what we were hoping when, we began to understand the scope of the PFAS problem was that we could take these technologies that, many folks have been working on for dozens of years now, but that simply wasn't the case because of how resistant to break down these contaminants are. And so common ways to treat PFAS that are also applicable to lots of different other contaminants. It depends on their chemical properties, but generally speaking, ways to manage PFAS are you can separate them from the water so you can absorb them onto something. One way to do that is pump the water up above ground, pass it through, let's say, carbon or other types of media that will pull the PFAS out of the water. Clean water flows out. But as I mentioned, all of that pumping can be energy intensive and expensive. Right now, that is the standard practice. It does provide treated water that is safe for people to drink. And so I don't want to imply that there's anything technically wrong with that. We were just simply trying to come up with something that's more efficient and also permanent. So when you separate PFAS from water, you now have a carbon or other type of media that now has concentrated PFAS on it that you still have to manage. And there's ways of doing that, but that's also expensive. And then it also takes your liability off of your site. So if I'm sending these PFAS-laden carbon to an incineration facility or a specialized landfill, even if that is a safe and healthy thing to do, you're taking that contamination, thus your liability off site. You may potentially be spreading that contamination elsewhere. So we wanted to develop something that would stay fully on site and prove to be at least more energy efficient, which is then also economically more efficient to have it all implemented right there on site. So another approach would be to inject something like a carbon or another adsorbent down into the groundwater. And those things that you can inject, they can stick to soil and hang out. So you can spread out carbon in the subsurface, for example. And as water passes through there, that will also pull the PFAS out of the water. And so, you can have treated water continue to flow. That has advantages because you're now not having to pump all of that water up above the ground. But there are still concerns about that, what happens over the long term. So we focused on developing a destructive technology, something that would permanently break down PFAS.
Now, that all makes sense. Thank you for explaining that. So you've got a website, of course. It's remwellrt.com, remwellrt.com. And the reason I mention that, in case people are listening, and they are, of course, is you can see a picture of a cylindrical device called the insert reactor. And insert stands for in situ remediation technology. So Michelle, without giving away any trade secrets, of course, can you explain what this device is like and how it's made?
Sure. So we are patent protected, so I don't need to worry about giving out trade secrets. I'm really happy to share how the technology works. So we are working with a partner, and I'd like to give a shout out to Blackstone, a transducer company that makes these ultrasound transducers. We've been working with them to take one of their off-the-shelf products and adapt it so that it can be operated underground. So we're talking about wells that might be 500 feet long, and you put your reactor in the middle somewhere. And so you need cables, power cables that are 250 feet or more long to come up to the surface. So that's an example of one adaptation that we needed to make. We also have to make sure those electronics underneath the ground, that they don't get exposed to water and that they can be cooled. So we've worked to make sure that those design features are incorporated. And it also has to fit into a cylinder. So we designed a housing for it that would not negatively impact how the sound waves break down PFAS. So the way the reactor works is contaminated water comes into the well. It flows through the reactor and over this ultrasound transducer. It's powered above ground. It runs continuously. And ultrasound in water will cause cavitation. So it looks like bubbles, but they're actually cavities in water. And just like bubbles, though, they can only reach a certain size, and it's tiny. You can't even really see them. They reach a certain size, and they're no longer stable. They collapse. And when those cavities collapse, they release localized, really high energy. And that high energy is what can break down those PFAS compounds. So we had to make sure the geometry worked well. It's not hard to imagine if you picture throwing a stone into a lake or a pond. We all know how the waves ripple. Depends on what other barriers might be there. That same thing happens with sound waves. So we had to make sure we had a geometry that would work for sound waves and still enable cavitation in that confined underground setting.
Wow. So let's talk a little bit more about the wells. You mentioned horizontal wells before. And why are they better than vertical wells, again, for PFAS remediation? What are some of the advantages to going horizontal with this approach?
Yeah, so the way the horizontal well works is you can think of it as an empty pipe under the ground, and it's surrounded by soil, and the water can move into that empty pipe a lot easier than it can move through the tortuous pathways around all of the fine soil particles. So a well that might be 10 inches or 12 inches in diameter can actually capture water that's 30, 50 feet or more away because it's the path of least resistance. So it's called flow focusing. So it will capture a lot of water, and you don't need to provide energy necessarily to capture that water. It just, if you put it in the direction of groundwater flow, then it will capture that water. So how much water it captures depends a lot on the subsurface properties. And so you need to really match your well conditions to the site properties. In other words, it isn't going to work for every single site under all conditions, but frankly, no treatment technology works at every site under all conditions. And so, we were inspired by Arcadis has a patent on the reactive media horizontal treatment well. And that's what I was talking about earlier, the project that we were working on, where that water then passively flows in. It passes through a reactive media, in the case of Arcadis, our partner in their patent conditions. And that media passively treats the sample, clean water flows out. So we are providing energy into that system in terms of the reactor itself. It's like running a refrigerator. It's plugged in all the time and it runs all the time, but it's not super high power, super high energy. But we don't have to provide the energy that's required to pump water up against gravity out of the ground. And so it's that passive capture that's really appealing. You can avoid that energy intensive pumping.
Sounds good. And of course, there'd be a cost savings with that, I would imagine.
Yes, and so that's where our savings and operating costs, which again, how much it saves will depend on site-specific conditions, the size of the site, but on average, we present significant cost savings because of that savings in the energy requirement to pump water at a pump and treat site.
Excellent. And of course, developing this technology costs money. Everything does. And you've had some help along the way. And one of the things that's happened is Remwell entered the FUSUB commercialization competition in 2018 and won a grant for $50,000. How did you use that award, and how did it lead to additional opportunities to attract investment?
Yes, so that award was everything for us. Before we won the commercialization competition, the insert reactor was an idea. It was an idea on paper, and it was something we really wanted to bring to life, and that's what that $50,000 allowed us to do. So it bought us our first transducer and our first housing, and that enabled us to start testing in the lab. We were really, really pleased with those initial lab results. And so we were able to start bringing it all to life and moving forward to apply for an EPA SBIR project funding.
Yes, and that's very exciting. They're very competitive, and my understanding is you've been awarded Phase 1 and Phase 2 SBIR awards. How have you used that money to advance your technology?
Yeah, we're just getting ready to wrap up our Phase 2 award. And we've used those SBIR funds to really work through our second and our third prototypes to now what is the design we're using in the field as we speak. And we were able to adapt that reactor from the laboratory setting where I can just take that transducer, kind of put a simple housing on it and plug it into the wall, into the much more robust system that we now can put underground and 250 feet or more down inside of a well. So, the adaptations it took to power that. And we've also added automation functioning. We have sensors built into it now where, let's say, if our heat gets too much, then it will automatically shut down. If we detect any leaks, it'll automatically shut down. And it also enabled us to partner with the Army Corps environmental labs. They're called ERDIC, and those folks are amazing. They're really incredible field engineers. So they were the ones that were able to help us translate our ideas that were pretty much academic in nature at the beginning of all of this. And again, bring that all to life into what we can actually install in the field.
Sure. And you mentioned the Army Corps of Engineers, and I read on the FUSUB website, there's a success story, of course, about Remwell. And what I read is the Department of Defense is also interested in your technology. And it struck me as something very interesting because clearly this is not a weapon system. So why is DoD interested in this?
Yeah, that's a great question. So I mentioned that PFAS have been used in a wide variety of industrial and commercial products. And one of those that has led to a really widespread contamination is their use in firefighting foams. And so any organization that has, engaged in firefighting training, as you can imagine the DoD would, over many years, they have a PFAS contamination problem. So the DoD is actually the largest funder of environmental research. Many might be surprised to know that, but in addressing the PFAS problem very specifically. So they've been proactively funding not only some of this work, but the work of many, many others in developing solutions to address the PFAS problem. So the DoD is funding a field demonstration. We've recently installed the reactor at one of their sites, and I'm sitting here literally awaiting data as we speak to see how it's all working. So we were able to successfully install it. We know that it's running and operating in the field. And, we have remote sensing, so I can look up online and see that it's running as we speak. And what I don't have yet are the PFAS destruction data that will tell us that it's performing as well as we hope. So hopefully we can have a little follow-up discussion someday, and we can let you know how that's looking.
That would be great. And it's all about the data. And you've been very transparent in our discussion today about the amount of money that you can save. And on your website, it says that your technology can save 40% in annual operating costs. Tell me more about that. How did you come up with that number compared to carbon treatment?
Yeah, there's a lot of historical information available in the literature and through EPA websites and elsewhere about the cost of pump and treat systems. It's an approach that's been used for many, many years. And as I mentioned earlier, while we don't always use that as the approach for more easy to treat contaminants anymore, it is right now the standard for PFAS as some of these emergent technologies come online. And so we were able to take, that information. It sort of summarizes costs associated with pump and treat on average. And so we could take a site with typical PFAS contamination characteristics, and we could design a pump and treat system, and we could do a conceptual design of our system. And we have a design tool that helps us understand, how many reactors would be needed based on the scope and scale and size of the site. And then we also have a cost calculator tapped onto that design tool. So we could do a pretty high level cost estimate. And, we arrived at 40% or more savings in annual operating costs, mostly due to the savings from not having to pump the water out of the ground. But there's also less maintenance on average. You don't have your disposal costs and other factors as well. Now, when you take sites of different characteristics, different sizes, and so forth, we still demonstrate savings, but it really depends on the concentration of the contaminants, the size of the site, the soil properties, right? How much water we can capture per well, and so forth. So I do want to emphasize that it is site specific. But on average, we anticipate that we can save 40% in annual operating costs. But that high-level cost estimation based on those site-specific characteristics is something that we can talk to potential customers about ahead of time. So we could estimate what that would look like on a site-by-site basis.
Excellent. So let's talk, last question, about some of those potential customers. Back in October, I met one of your colleagues at the New York State Innovation Summit in Saratoga. And I remember learning that you have a product launch planned for 2024. Can you tell us about that?
Yes, so as I mentioned, we're anxiously awaiting these site data. We have another demonstration coming up at an international site, and those data should be coming in probably in the earlier part of 2024. And if those data look like we expect, then certainly we're going to take advantage of those to tell our story and to do a major product launch. So through our field installation, we've learned a couple of more design tweaks, for lack of a better word, that we want to make, really about making it easier for the drillers that have to install this and get it to the place it needs to go down the well and so forth. And we anticipate those design changes will also take place in early 2024, and that we are ready with the product that can truly go to market here in probably the second quarter or beyond of the year.
Excellent. I look forward to hearing more about your progress.
Thank you. I look forward to telling you more about it.
Good. Dr. Michelle Crimi, thanks so much for being on New York State Manufacturing Now.
I appreciate the opportunity. Thanks so much, Steve.
You got it. So we've been talking to Dr. Michelle Crimi, co-founder of Remwell in Potsdam, New York. If you're a New York State technology or manufacturing company, you'd probably like to learn more about the FuseHub manufacturing grant that Remwell won. More to the point, you're probably wondering if you too could be an awardee. Well, as the hockey great Wayne Gretzky once said, you miss 100% of the shots you don't take. So get a stick on the puck next year and give it your best shot. 2024 will be here before you know it. So make sure that you're on FuseHub's email list to get updates. Just go to www.fusehub.com and click the green subscribe button at the top right of your screen. On behalf of FuseHub and New York State Manufacturing Now, this is Steve Melito signing off.